And welcome Calculus 3. Today we are going to extend our definition of area under the curve to volume under a curve in 2 dimensions. You'll notice that we are doing this with respect to both an x and a y. It extends that same definition of a Riemann sum. And what we're doing is we're making these little boxes, and we're finding the volume of each of these little boxes, and we're making each of these boxes as close to 0 as possible, making the size of these boxes as close to 0 as possible, and then what we're doing is adding all of those volumes up. And this will be in 2 directions, an x and a y direction, with the z being our function. So in example 1, we want to evaluate this volume, and we're given that the area function is a function of x, and we're going to integrate with respect to y. So area of x, and if I integrate this with respect to y, I'm going to get 6y minus 2xy minus y squared over 2 evaluated from 2 to 0, and I'll punch that in. Alright, so our area from 0 to 2 on the on the y is 10 minus 4x. Now our volume, we're going to integrate from 0 to 1 this 10 minus 4x with respect to x. So we'll get 10x minus 4x squared over 2, and this will be evaluated from 1 to 0. Plug that in, and we get an 8. So our volume is then 8. In example 1, this was the entire operation that we performed, where we did this inner integral, and then we computed that, and then we did the outer integral. In example 2, we're wanting to do the exact same thing. They want us to compute the volume again, but this time they want us to do it, instead of the inside being the y, they want the inside to be the x. So I'm still going to have, if I'm looking at the area for the x, the inside integral, the x is still going to vary between 1 and 0 for this function. And then this outside, when I go from y, the y is still going to vary between 2 and 0. And what they want me to do is verify that it doesn't matter which order I choose, whether I'm going to choose to integrate with respect to the x or the y first. So I'll go ahead and get this, and our answer had better be 8. And when you do this integral and you get it completed, you do find that the answer is indeed 8. From example 2, we get the following theorem, where it doesn't matter in which order we perform this integration. Just be sure to keep your limits of integration with the appropriate respect, whether it be the x or the y. In example 3, we are to find the volume, and we are supposed to integrate with respect to x and then y, and then also y then x, and we're supposed to show that we get the same answer. So let me get that set up. Alright, and if you'll notice, these limits of integration go with the x, and I'm going to integrate with respect to x first, then I'll integrate with respect to y. This one is set up to integrate with respect to y, and those limits of integration are y values, and similarly I will then integrate with respect to x, and these are how the x is bounded. Alright, and I'll get that done. Alright, and there's the computation, and it doesn't matter which way you do it, you still get an answer of 32. So in example 4, what we're going to do is try to figure out an easy way to integrate this, and note this natural log of 2 here. So I'm going to figure out which way would be the easiest if I were to integrate this thing. So let's set it up both ways. So with this first setup, I was integrating with respect to y first and then x, and it involves an integration by parts. And when I started down this road, then I got to this point where I'm going to have some more integration by parts, and it's going to get pretty messy. So I tried it with the other method where I integrated with respect to x first and then y, and it just fell out beautifully. So if what you're doing gets really messy, try going at it the other way and see if that'll work for you. And I'm not going to finish the other one. In this very last example, we are given the definition for average value, and we are, in order to get that average value of our function f, we are to first compute the area of R. Well, it is a 2 by 2 rectangle, or actually a square, so that would be 1 over 2 times 2 is 4. And then my integral, looks like I can do it either way, so I'll just, and both of them are from 0 to 2. So it doesn't really make any difference which one I put first because they are the same, so I'll just do this. I'll compute this integral and get the average value. Alright, here I have integrated with respect to x, then I'm going to plug in my 2 and my 0 in for x, and I'll do my regular definite integral, plug in for 2 minus whatever for 0, but it's just going to be 0, so that's not really going to affect it any, and then I'll integrate with respect to y, and I'll be done with this guy. Alright, the average value for this particular function over this plane region is 0, and that's because it is symmetric. And if you have any questions with this, be sure and see me at the Collaborate or send me an email.